In this chapter 3, we'll introduce determinants and consider some properties of determinants. Here we have section 3.1, Introduction to Determinants. The metric A is an n by n square metric. Then determinant is a scalar value denoted by dta, or we may use absolute sign, so in this way. When A is on 1 by 1 metric, so it has only one entry, the determinant of A is A, the entry. And if A is a 2 by 2 metric, A, B, C, D, then the determinant of A is defined to be AD minus BC. This cross product and difference is measured AD minus BC. Okay, let's see this example. A is now 2, 1, 0, 3, and we consider a linear transformation T, and given by this metric multiplication. T of x is ax. Now, part 1, find the determinant of A. Determinant of A is AD minus BC, 6 minus 0, which is 6, right? We found the determinant, and determine the image of rectangle and under T. Okay. Metric multiplication is a linear mapping. So the line goes to line, corner goes to corner. So here for part B, we try to visualize the domain here, that one, the rectangle, that is another 0, and that is 2, and that height is 1. Okay, we'll try to indicate the point by using two coordinates. There is 0, 0, and that is x equals 2, y equals 0. That will be x is 2, y equals 1. And this one will be 0 and 1, right? So that is the region. We want to find the image on the T of this region. Okay. This is xy coordinates. Okay. Now 0, 0 will go to 0. Okay, we put here. We name the points. This is number 1 point. There's number 2 points. Then number 3, number 4. Okay, so that one is image of number 1 point. And how about number 2? Okay, here the metric is 2, 1, 0, 3, and here 2, 0 is multiplied. Then we can easily get that multiplication is 4. The second row multiplication is now 0. So that, and from here we have 4 and 0. Okay, that is the image of number 2 point. Okay, that is now here 4. That is number 2 point. Okay. Now for third point, we put here now 2, 1. That point. Then this multiplication will be 4 plus 1. So that is now 5. Okay, and then now this multiplication will be 3. Row, column, and 5 and 3, that is 5, and height is 3 here. That is 5.3. That point is number 3 point, image of the number 3 point. And for the last one, 0, 1. Okay. 0, 1 is multiplied. Then you can easily see that's the second column. It's 0 and 1. So only second column, 1, 3. Okay. Here we have, here there is 1 and 3 height here. Okay. That's a fourth point. If we make the corresponding shape, then we have this one, 1, 2, 3, 4, and coming back to 1. Okay. Now that's the image of the rectangle. Find the area of the image. Okay. Bottom length is 4, height is 3. So here, that is now 12. Okay, we write down here 12. Quite easily you can get it. Now, figure out how determinant of A, which is already we know that is a 6, right? And the area of rectangle, that is 2. And the area of image are related. That is now 12, right? And determinant is 6. And the area of original rectangle is 2. And the area of the image on the transformation is 12. So 6 to 12 looks like this 2 multiplication is 12. The rectangle of area 2 is transformed into area of 12. In fact, that is parallelogram. And now you can easily see that multiplication is 12. So this is not accidental case and always happening. So we can say here now the determinant can be viewed as a volume scaling factor. Okay. Okay, here now Aij is the sum matrix of A obtained by deleting row I and column J. So we try to use the notation Aij for such a sum matrix. And Ij cofactor of A is scalar value given by here, minus 1 to the I plus j, and determinant of the sum matrix. So here pictorially, we can see here now. And for example, this is a 3 by 3 matrix. And if we consider Cij for that matrix, then, okay, more specifically, rather than Cij, okay, let's consider here for that one, this position, this is 1, 2 position, C1, 2. Okay, that is same as minus 1 to the 1 plus 2. Ij is 1, 2, so 1 plus 2. And that is determinant of A1, 2. That is sum matrix. The sum matrix is made here after deleting row containing that 5 and column, and so that will be determinant of, if we delete this row and column, then the remainder part is 2 minus 1, and now that is 0 and 0. Right? 2 minus 1, 0 and 0. Okay. So determinant of this 2 by 2 matrix is 0, so that for this one, the value is 0. C1, 2 is 0. In this way, we define cofactor, and that is 1, 2 cofactor for 1, 2 position. Okay. In this way, we define cofactor. then now we can define determinant of an n by n matrix for general n larger than or equal to in this way. It's a cofactor expansion here across the first row. So determinant of A is A11 times the corresponding cofactor C11. So in this case, A11 is 1, and we can find the C11 similarly for that one. And then A12, that is 5 times C12. Here for this problem, C12 is 0. And we go to the last one in the first row, and A1n times C1n. That is cofactor expansion using the first row. But this cofactor expansion can be made any row, second row, and the third row, and for general n by n, any row cofactor expansion is the determinant. That means that this quantity is always the same independently of the choice of row. Now also, this cofactor expansion can be made down the column, so that any column, and column J, first column, second column, third column, it doesn't matter. And always, if you try to get the quantity, the determinant, then it will be the same. So determinant of general n by n matrix is defined in this way. Here the advantage is that, okay, for example, A is in a 30 by 30 matrix, then for cofactor computation, we need 2 by 2 determinant of 2 by 2 matrices. But that we know already, just AD minus BC is the determinant, so that we can get determinant of 30 by 30 matrices. Now, how about 4 by 4 matrix? Then for that one, now cofactor requires to decide the determinant of 30 by 30 matrices. Now, also we know already, so that we can finish along with a cofactor expansion either through row or column. We can get here the determinant. So we can apply recursively by using this cofactor expansion, so that for any n by n, we can get determinant. Okay? Okay, that's the definition of determinant. Find the determinant of A by expanding across the first row and down column 3. Okay, here, okay, we try to find the determinant with across the first row and down column 3. That's the first one, second one. Okay, for first part, the determinant of A must be here 1 times A11 times C11, okay, C11, plus 5 times C12 plus 0 times C13. Okay, we already got C12, and that's 0, so we can eliminate this one. And this is 0, so we don't have to get C13 because already we have 0, so that's 0. Now, only required one is C11, 1 times, okay, minus 1 to the 1 plus 1, that's 1 and 1. And here, the minor, the submatrix is, now we eliminate row and column for this value, this position. Then the remaining part is 4 minus 1 minus 2, 0. So 4 minus 1 minus 2, 0. Right? So determinant of that one is 0 minus, okay, the multiplication is 2, so minus 2, 0 minus 2, so minus 2, 1, 1, so 1 times minus 2, which is here minus 2. That's the determinant of the matrix. How about second part? Okay, now if we are using the down column 3 for the determinant of A, then 0 times C, okay, 1, 3, there's 1, 3 here, and there's 2, 3, plus minus 1 times C, 2, 3, and plus 0 times C, 33. Okay, yeah, because this is 0, we don't have to worry about it. Also that one. Now, this one is same as minus 1 and minus 1 to the 2, 3, 2 plus 3, and then now there's a determinant of 2 by 2 matrix. The sum matrix can be obtained by deleting row of minus 1 and column. The remainder part is 1, 5, and 0, minus 2. Okay. Minus 1. Okay. Minus 1 times, again, this is minus 1. And determinant is AD minus BC, which is minus 2. Okay. So that is minus 2. And here, across the first row or down column 3, we have the same result. But apparently, and this down column 3 is easier because you have more zeros, so that you don't have to worry about this portion, that portion. Practically, you may write that on, you may ignore these two terms. You don't have to worry about it, right? So that you can get the determinant more easily. And also, if you try to use the third row, then also you can get the determinant quite easily. You have to consider only this single term is more effective, and you can get it more quickly. Okay. Okay. Now compute the determinant of A by a cofactor expansion. Okay, here, and you can see here now, third row has only the single non-zero one, so that we may use that one. So here, determinant of A is 3 times. Now that is a 3 by 3 position, C33. Okay, that is now 3 times minus 1 to the 3 plus 3, and now determinant of the sum matrix after eliminating row and column, we have 1 minus 2 and 2, right? And 2 minus 6 and 5, and here 5, 0, and 4, right? Let's try to visualize here. That eliminated, and remaining part is 1 minus 2 and 2, 2 minus 6 and 5, 5, 0, and 4, right? Okay, again, now you have to get determinant of this matrix. Now here, last row has 2 non-zero. Okay, there we have 1 0 here, so that the cofactor expansion can be done along with the last row, so it's much easier. Okay, for that one now, determinant of this one is now 5 times here minus, okay, cofactor is C. Okay, now we focus on that one, C31 plus 4 times C33. Okay, that is same as 5 times minus 1 to the 3 plus 1, which is 1, so we ignore that. So here that sum matrix is minus 2. Okay, eliminating this column and row, minus 2 and 2, and minus 6 and 5, right? And plus 4 times minus 1 to the 3 plus 3, which is 1, and here the sum matrix, determinant of sum matrix, 1 minus 2 and 2 minus 6. Okay, for this one, for that entry, we eliminate row and column, and the remaining part is this one, right? Okay, so for that one, 5 times here, minus 10 plus 12, so it is a 2, plus 4 times, now minus 6, that's minus 6, and plus 4, so that minus 2. Okay, minus 6 plus 4, so yeah. So it's minus 10 plus 12, okay. So here 10 minus 8, which is 2. Okay, so this portion is 2, so we can conclude the quantity. There's a 3 times 1 times 2, which is a 6. Okay, that's the final answer. If A is a triangular metric, lower or upper or lower triangle metric, then determinant of A is the product of entries on the main diagonal of A. Let's see this example. This is upper triangular metric, and if you are using Cofactor expansion for the first column, then 1 times, so that here now determinant of A is now A. Determinant is 1 times the sum matrix in this portion. Now minus 6, minus 7, 5, 0, 3, 0, 0, 0, 4, right? And these are zeros, so that you don't have to worry about it. Now, we focus on this matrix. Now, this is now C11, and except, okay, A11, except this one here 0, so that now that is equal 1 times minus 6 can come out, and here the minor, determinant of minor, which is 3, 0, 0, 4. Of course, right now, we ignore the minus 1 to the 1, 1, 1 plus 1. Okay. Now, for that one, the determinant is 12. So, in fact, product of that one. So, 1 times minus 6 times 3 times 4. That's the determinant. That is exactly the same as the product of diagonal entries. Right? Upper triangular or lower triangular, the logic is the same. Okay, we have here true or false problems. Okay, now on n by n, determinant is defined by determinants of n minus 1 by n minus 1 sum matrices. Is it true? Yeah, it's true. That is cofactor expansion, but each cofactor need to get determinants of sum matrices, right? Okay, the ij cofactor of a matrix A is the matrix Aij obtained by deleting A from A is ith row and jth column. Is it true? Okay, ij cofactor of a matrix A is a scalar value, not a metric. And in the definition, cofactor is minus 1 to the I plus j, and here determinant of the submetric Aij. So the cofactor is not a metric, but a quantity in the following the definition. So the statement is false. The cofactor expansion of determinant A down a column is equal to the cofactor expansion along a row. Yeah, it's true. Any row, any column can be chosen to get cofactor expansion, but you may try to choose the simplest one. That means that a column or row which has most zeros, right? The determinant of a triangular metric is the sum of the entries on the main diagonal. Okay, it's wrong, right? And rather than sum, you have to do multiplication. The product of main diagonal entries is the determinant for triangular matrices. Okay, this is the end of the section. Thank you.